Today I have something different for you. Instead of just going through the new Swift charts, I decided to use it to visualize the sorting algorithms. So this is what we'll be building. The bubble sort. Selection sort. Insertion sort. And a quicksort. Swift charts is a really powerful SwiftUI framework. It will definitely help to visualize your data. You can easily build custom charts with a minimal code. We will start with a really basic Swift chart example, and then I will talk and explain each sorting algorithm that you just saw. So let's check the documentation. Here you can see that it is really simple to start with the Swift charts. You basically need to import charts and create a chart and add here a marks. The basic one is the bar mark, and it looks like this. You need to provide the x-axis value and the y-axis value. So this is the x1 and the y. And as you can see, it also exports groups. Okay, let's go to the Xcode and create a sample chart. Here we have an empty SwiftUI app. Let's add Swift charts. You need to add import charts and then create a chart. Let's add a bar mark. And as you can see, we have a very simple one bar mark here in the Swift charts. Let's add the frame to the chart so it will look a little better. As you can imagine, you can add more of those elements. So we have a very simple SwiftUI chart. Okay, let's add some input and present this on the Swift chart. Let's create an input. This will be our seed data. We'll just use this one to actually propagate this inside the charts. Of course, you can, in the real app, you can have like data delegate or like any other input type. This one is just for, testing. Let's create the state variable so we can store the data and actually present this inside the charts. Now let's remove those and create a for each loop so we can iterate over this data that we'll be using for presenting the charts. Let's create an array and zip it on the data. We'll use the indices to get the data with the index. So the indices is a subscript of the collection, so it's basically like an index. And we are zipping this with the data. So we will get an index and our item. And the SwiftUI will tell by the ID which element it is. So we are here just using the index. Okay, now on up here we can load some data. Let's fix the position, add the index and the item. So now we have our SwiftUI chart. Of course, at this point it's all sorted, so let's make this shuffled. This chart will present all of the elements from 1 to 30, so there are no repeated elements. Okay, so right now we have the basic SwiftUI chart. Let's go back to the sorting algorithms. We will start with the bubble sort, which is probably the most straightforward sorting algorithm. It is a comparison-based sorting algorithm, which means that we will compare each element and check which one is bigger. The bigger elements will bubble up to the right side. And because we will do a lot of comparisons and compare each element of the array with the other elements, this algorithm is slow. In fact, all of the algorithms that we will use with Swift charts here are slow and do a lot of comparisons and array swaps. ON square time complexity is not a great performance, so we definitely should know to use this in a production app. But for charts visuals, it works really well. Okay, let's check the example. So we will start with comparing two elements. 7 is bigger than 4, so we will swap those. Then compare another two elements. 7 is bigger than 5, so we'll swap it. And then compare another two elements, and 7 is bigger than 1, so we will swap it. And we'll go back to the beginning. 4 is smaller than 5, so we are not swapping it. 5 is bigger than 1, so we will swap it. And because we know that 7 is in the correct position, because each iteration the element will bubble up to the right, so 7 is in the correct position, so we are no longer checking 5 and 7 because we obviously know that 7 is in the correct position. Let's go back to the beginning. 4 is bigger than 1, so we'll swap it. And that's all, our array is sorted. Okay, let's implement it. First, we need to check if there's more than one element, because if there's just one element, the array is already sorted. Then let's iterate over the array. So this is the first loop, and inside this loop we need to create another loop. So inside the second loop we are extracting the I, because we already know that each pass will bring the last element to the end, so we don't need to do this additional check. Now let's compare both elements. Okay, so if the first element is bigger than the second one, let's swap it. Now we can run it. Let's add a button which will invoke the bubble sort. And we can run it in the SwiftUI preview. Okay, so it works, but we would like to see how this sorting is being performed. To actually see how the algorithm is sorting those elements and how they are moving, we can ask something like task sleep. Let's do this. So after each swap, let's ask task sleep. We can use the new until with the new syntax, because we are using the iOS 16 with the Xcode 14. We need to add try and await. And the whole function needs to be async and throws. Now the bubble sort needs to be also performed asynchronously, so let's wrap it inside the task. Don't forget to add try and await. Now let's see how it will go. We added the 15 milliseconds after each swap. You can see that each element is, the bigger one is bubbling up to the right, going there. Let's maybe add 1 second and see how it goes. Okay, 1 second is a little too much, half a second. You can see the biggest element is going to the right, then it will switch to this one. This one is going to the right, it bubbles up, it's the last element, and it just repeats the cycle. And this one will go. up here. Okay, this looks nice, but what if we could change the colors and see maybe this element and the next element in the different colors? Let's add some colors to this one. So let's create a variable with the state. So this one will be our active value, the one that we are currently comparing. And the second one will be the next value that we're really comparing with. Let's set them during each iteration of j. Now let's create a function that will return colors. So if the value equals to the active value, let's return a green color. If the value equals the previous value, let's return the yellow color. Otherwise, we will default to blue. Now to use the colors, let's set the foreground style on the bar mark. And let's switch it to gradient. It looks a little better. Let's make it 50 and let's run it. As you can see, we have the yellow and the green one. Okay, those two needs to be reset. After the sort, let's set the active value to 0 and the previous value to 0. What would be nice is that after sorting, we could set all of the elements to green. So it could go from the first to the last element and highlight each element and change it to green. So let's add additional state. Let's make it optional. Inside the colors, let's unwrap the check value. And if the value is smaller or equal to check value, we will set it to green. So now after sorting, we'll just iterate through the whole array and set the check value to the value of each element. And also let's add a little delay here. Okay, let's run it. Okay, that's much better. Now to make this even better, we will add a little sound, the tone, a beep, during the sorting. So you can also hear the sorting, which is really cool. I used this sample code from Apple, build a signal generator. You can download it from this website. I will put the link into the description. I already have it inside the project and I made some changes inside. So there's the frequency, so if you will provide a value to the beep, it will actually modify this. It sounds a little better. Also I added a timer, so it will not cut off really rapidly. It definitely can be improved, so feel free to play with it. Okay, so let's add some sounds to our sorting algorithm. So here, before each swap, let's play a sound. And also here. And because the sound cannot be played in the background, I mean it can, but it will make a lot of weird noises. So let's add a main actor and play this on the main thread. Let's change our sleep function a little bit because it will be a little too long, I think. Okay, now let's play it, but because I had some issues with the SwiftUI previews, let's play it inside the iOS simulator. Okay, so that's the sound of the bubble sort. Selection sort is also a comparison-based algorithm. It follows the basic idea of the bubble sort, but the number of swap operations is reduced. But it is also slow. During each pass, selection sort will find the smallest unsorted value and swap it into place. The first loop will start with 0, but will not iterate up until the last element, and that's because the last element, since all of the other elements are in place, it will be also in place. During each pass, we will set the smallest element to be the same as the sorting index. Then we'll compare the smallest element with the next one, and then we'll check which element is smallest. Here 4 is smaller, so we will set it as a smallest element. Then we'll do the next comparison. 4 is smaller than 9, so we will switch to another one. And here 1 is smaller, so we will set the smallest element to be 1. And after the pass, we will check if the smallest element is not equal to the sorting index. In this case it's not, so we will swap it. And then next loop, the sorting index will be 1, and we'll set the smallest element to 4. We will compare with 9, it is also smaller, and we'll compare with 7, and 4 is still a smallest element. So next one, we'll compare 9 with 7, 7 is the smallest, so it will be the smallest element. And because the smallest element is not equal to the sorting index, we will swap it. And that's it, our array is sorted. Now let's write the implementation. First of all, let's remove the bubble sort. And let's create a new one. As I said, the first loop does not have to include the last element, because after sorting, the last element will be already in place, so we can skip this one. Let's set the smallest element to the sorting index, and let's create a second loop. So the second sorting will start with our sorting index plus 1, so the next element will be compared. So let's compare the smallest element with the next one. And if the item with the smallest index is bigger than the next one, we need to set the smallest index to the index of the next one. So smallest index equals j. And then we need to compare and check if the smallest index is not equal to the I. And if not, we need to swap those elements. Don't forget to actually run it. Let's add it here. And let's run it and check if it actually works. Okay, so it works, and let's add some pauses and fix the visualization. Let's add the active value here. Don't forget to add the beep sound and a sleep for 20 milliseconds. And let's add the active value here. Previous one set to smallest. And add the sleep. Okay, let's run this again. Alright, it all works. Let's switch to the next one. Insertion sort is an interesting algorithm. It is still slow, but for the right data it can be even ON in terms of the performance. And the right data is the one that it is already sorted. It is somehow a reverse bubble sort, as smaller values are set first, and it will go up to the right. We'll start with the sorting index as 1, and then the second loop will start with the reversed values, so it will go from right to the left. First we'll compare two elements, and 4 is smaller than 9, so it will be swapped. Then the sorting index is up, and we'll compare those two elements. 7 is smaller than 9, so it will be swapped. And then, as I said, from right to left, we will compare those two elements. And those are in a good place, so we'll not do anything. And we'll increase the insertion sort. So this will be the next iteration. So here we are comparing 9 with 1. It will be swapped. Then we are going with the reverse direction. So 1 will be compared with 7. It will be swapped. And once again, this will be swapped. And that's it. The array is sorted. This may not be so obvious, but yeah, let's write the code and you will see. First, let's delete the selection sort. The first loop goes from the first element up to the last one. And the second loop is a little different. We will use the first element up to I, which is the sorting index, and we will reverse it. This way, as you saw, we will go from right to the left. So if the first element is smaller than the second one, we need to swap it. And if not, we can just use the break to exit this loop. Let's also set the active value, previous one, and add sound. Okay, that's it. Let's run it and see how it will go. Cool, let's check the last but not least, the quicksort. Quicksort is a comparison-based sorting algorithm, so it is similar to other algorithms that we use so far. What's the difference is that it uses a divide and conquer strategy and recursion. It means that the algorithm will look for the pivot point first, then it will split the array into two parts, and if necessary, it can keep splitting and calling itself. Let's go to the Xcode as it will be more clear when you will see the code. Let's remove the insertion sort first. Because it is a recursion-based algorithm, we need to add an array that we'll be using as an input variable. We'll use in-out, so we'll be operating on the array that we will pass into the function. The low and high are the indexes that we'll be passing into the function that we would like to operate on. So first we need to check if the low index is smaller than the high index, because otherwise, if we will call this again, and we will be calling this again and again because it is the recursion, it will just keep going and our app will basically like freeze. So first we need to get the pivot point. And we need to pass our array and the low and high index. Because we don't have the pivot point function yet, let's create one. And because our pivot function will return the index of our pivot, let's return an integer here. Whoops, we have a typo. Low and high and low and high. Okay. So we have the pivot and let's use the recursion here. We need to operate on our array and we need to pass the lower index here and the, and the pivot point -1. So this quicksort will call itself with the left side of the array. So if we will have a pivot point here, this one will be the left side of the array, and this one will be the right side of the array. And both of those will call a quicksort, so it will be a recursion. So let's call the right side. So it will be the low index will be pivot +1 up until the high index. Okay, so right now we need to write a pivot function. There are many different implementations of the quicksort algorithm. What we'll choose here is the Lomuto partition scheme. It's not the most efficient one, as it does more array swaps. But that's actually a good thing, as more swaps means that the visual part of the sorting will look more interesting. The pivot function takes the last element as pivot, places the pivot element at its correct position in sorted array, and places all smaller than the pivot elements to the left of the pivot and all greater elements to the right of the pivot. So our pivot element will be set to the last element of the array. Let's check the example. So here our pivot will be set to the last element in the array, and then we will loop through all of the elements from the low index up to the high index. So the I is set to the low, and also we'll start with the j set to low. Then we'll compare the element that is on the index of j and the index of the pivot. And if the j element is smaller than the pivot, we will continue looping. So because the element under j index is smaller than the pivot, so we'll swap both the values of the I and j, like this. And then we'll add 1 to the I, and continue the looping. Then we'll compare 1 and 3. And because 1 is smaller, we will swap I and j once again. +1 to the I. And after the loop is over, we need to swap the element under the index I with the index of the highest element. So here it will be the pivot. So we need to swap the 3 and 6. So it is the index number 2. So we divided this array into 3 different arrays. So the first one is our pivot element, which is already in place. And we got on the left hand side 2 and 1. And we'll use the quicksort to sort this again. And on the right hand side we have 7 and 6, and we'll use the quicksort to sort this again. And so this is like a simple example. So after yet another quicksort, it will be all sorted. Okay, so let's write it. Let's set I equals low, and let's create the first loop. So let's create the loop. We'll start with the low value up to the high. So in this case, we'll start and loop through the whole array, but each time we'll call a quicksort, it can be that we can start a low from a different position. So it will not always be the same. It can be that the low will be 3 and the high will be 4. So each time we need to compare the value of the array element with our pivot value. And if the element is smaller than a pivot, we need to swap element j with our element I. And then we need to add +1 to the I index. And in this case, because we are using the in-out array, we also need to swap on our data here, because this is the data that we will use to represent our Swift chart. So also let's do this. We can also add the active and the previous value. Add sound. And add some delay. And after we'll finish the loop, we need to swap the element that is under I index and element that is under the high index. Also, remember about the data, we need to swap the same. And we can also add the active value, sound, and some weighting. Here, let's change it to high. And don't forget to return the I as an index from the pivot. So this is like the index that we are getting the pivot. So this is the index of a pivot element that we need to return here, and it will be passed and used to actually divide the array even further. Okay, let's run it and see how it works. And don't forget to add the main actor to the pivot, as it will break our sound. Here we could also reset our active and the previous value, as you saw, it was in a wrong state. Okay, let's run it again. I know that Swift charts are not designed for that kind of use case, but I thought that it would be fun to play with it in a little inconvenient way. Please keep in mind that those are not the most efficient sorting algorithms. I chose them because it looks interesting while sorting. I hope you enjoyed this video as much as I enjoyed making it. Thank you for watching and see you in the next one.